Okay, these are the contents of this video. So in this video we are going to look at synchronous generators, especially the rotor designs, the supply of DC power to the field circuit, the speed of rotation, and then the internal generated voltage, and then the equivalent circuit of this generator, and finally the phasor diagram of a synchronous generator. And the remaining topics on the synchronous generators will be covered in the part 3 video. Okay, in terms of construction of a synchronous generator, as with other machines that we look at before, it mainly consists of two parts, which is rotor and stator. In synchronous generator, a rotor magnetic field is produced either by a permanent magnet or by applying DC current to a rotor winding to create an electromagnet. So if you look at the illustration at the bottom here, so the middle part colored in yellow, is the rotor, and as has been mentioned, that this can be a permanent magnet or a winding that will function as an electromagnet. And in the usage of this generator, this rotor will be coupled to a prime mover. So the prime mover will provide the mechanical energy into the generator, and which makes the rotor to rotate, and then the generator can generate the electricity. In this case, specifically 3-phase voltage as the output. Okay, and the other part of this generator is the stator. In the stator, we've got a 3-phase stator winding, and this winding is where the voltage will be in use, and this winding is also called as armature winding. So if you look at the illustration again, these are the, as you can see, the one that I circled here, they are all this the stator windings, and the component in colored in gray, this bit here is the stator of this generator. For the rotor, there are basically two designs, which are salient and non-salient. Salient means protruding or sticking out. As you can see, we have the illustration on the left hand side here at the bottom. It's an example of a salient rotor design. And to make it more clear, if you look at this design from the end view, this will look like this. So, right, while the salient one or non-salient one, from the end view, the surface of the rotor will just look like a circular, smooth one. So these are the poles that are protruding, and that's why this type of this rotor is called as salient rotor design. Okay, with the salient rotor design, we normally use this kind of design when we have a number of poles, a minimum of 4. So if the number of poles is minimum 4, or the number is more, then we tend to use this design. While if the number of poles is less than 4, then we use the other type, which is the non-salient. And the example that we have in here, you can see that here we've got 6 poles on this design. For the generator to work, we need to supply a DC current to the field winding on the rotor, which is quite tricky as the rotor is rotating and is not stationary. There are two common approaches to supply DC power to the rotor. So the first one is by the means of slip rings and brushes, and you can see the example on the illustration. So this bit here will be rotating with the rotor, and we supply the power through this spring-loaded brush, which make contact with this slip ring, which will rotate with the rotor. The characteristics of this approach is that it needs regular maintenance, because the brush, these two brushes, will get worn out because it's rubbing against the surface of the slip ring. However, this is a cheaper solution, and normally we use this approach or this method or this solution for smaller machines. The second method is by a special DC power supply that is mounted directly on the motors or the generator shaft. Let's say generator here, and we call this system as brushless exciter, and we will see this in more detail in the following slides. Okay, this slide shows us a brushless exciter system. This kind of system is used for large generators, and we use this again to supply the DC power to the field circuit of the synchronous generator. So a brushless exciter is basically a small AC generator with its field circuit mounted on the stator and its armature circuit mounted on the rotor shaft. So this bit here is our synchronous generator, and here is the small exciter. And as we can see that the armature circuit of the exciter is mounted on the shaft, on the shaft of this synchronous generator. So which means that they will rotate together, while these two parts here are on the stator side. So the stator of the exciter is connected to the stator of the generator. Okay. Right. Okay. So what does this exciter do? As its name implies, this is an AC generator, so it actually generates AC voltage as well. So this is why we've got, if you look at the rotor side again, it's supplying three-phase voltage as the output, and they are fed into this rectifier. This is the rectifier, and the output of the rectifier is a DC voltage. So across this you've got a DC voltage, and this is supplied to the field winding of the generator, of the synchronous generator. So as you can see here, by using this exciter, which is a small AC generator, then we can produce the DC voltage that is fed to the field winding of the synchronous generator. Okay, and then by controlling the small DC field current of the exciter generator, it's possible to adjust the field current on the main machine without slip rings and brushes. As you can see, this solution doesn't need any rings and brushes because the exciter is mounted directly on the shaft of the synchronous generator. And yes, by using this field resistance, yeah, the adjustable resistor here, the variable resistor on the stator, if you can see on the left here, then we can adjust the field, the magnetic field, and the outcome is that we can then adjust the voltage output, yeah, of the exciter, and by doing so we can then control the output current of the rectifier that feeds into the field circuit of the synchronous generator. If you look at the system on the previous slide, you will see that the exciter actually needs a three-phase voltage as the input. We can make the system completely independent to any input or any external power supply. And if you see this, the illustration on the slide, then you will see how this can be achieved. In addition to the synchronous generator that we had and the exciter, we've got an additional system here, or subsystem, which is the pilot exciter. Yeah? The function of this pilot exciter is to provide this system here, the DC voltage, yeah, to the exciter field of the exciter. Okay, and again, this pilot exciter, the difference between the pilot exciter and the exciter is that the pilot exciter is using a permanent magnet for the to generate the exciter field, yeah, which makes this system independent of any external power supply. And this slide shows us an illustration or a picture of a rotor with an exciter field. This bit is the rotor, while the system in the box, in the blue box, is the brushless exciter that we have described in the previous two slides. Synchronous means that the electrical frequency produced is locked in or synchronized with the mechanical rate or the mechanical speed of the rotation of the generator, and it's governed by this equation that Fe, which is the electrical frequency, or the frequency of the electrical voltage generated, is equal to the speed times the number of poles divided by 120. Yeah. So as we can see here, that the frequency of the electrical output is a function of the speed of the generator. Yeah. It's directly proportional, which means that if you want to, for example, double the frequency, then we need to double the speed of the generator. Yeah. Okay, and at the bottom here we've got an example. If electrical power is generated at 50 or 60 Hertz, the generator must turn at a fixed speed depending on the number of poles on the machine. Yeah. For example, to generate a 50 Hertz power in a 4 pole machine, so number of poles is 4, then the rotor must rotate at 1500 RPM. For the internal generated voltage of the synchronous generator, we found already that the EA, which is the voltage induced, yeah, in a given stator phase is equal to K flux omega, where K is a constant representing the construction of the machine, and pi is the flux in the system, and omega is the speed of the generator. The K itself has got two different values depending on what is omega, as described or as shown on this slide here. The internal generated voltage EA is also directly proportional to the flux in addition to the speed, but the flux itself depends on the field current IF, which is flowing in the rotor field circuit, as can be seen on the magnetization curve below. You can see that here on the right hand side, on figure B, that's EA, and then on the x-axis you've got the field current. Okay, and on the left hand side, part A, you've got the flux against IF. So yeah, the flux is affected by IF, and it's quite linear within this linear region, and therefore EA also affected by IF. It's also a function of IF. For the equivalent circuit of the synchronous generator, in addition to armature reactance effect, the stator coil has a self-inductance LA or XA as the reactance, and the stator has a resistance RA. So the phase voltage is given by V pi, which is the phase voltage, is equal to EA minus JXIA minus JXAIA minus RIA. Okay, this is the self inductance, and this is due to the armature reactance. Okay, and often the armature reactance and the self-inductance are combined as the synchronous reactance, or XS. So XS is equal to X plus XA, and therefore the phase voltage can be written as V pi is equal to EA minus JXSIA minus RIA. So here is the equivalent circuit of a synchronous generator. Yeah. The part on the right is the armature circuit. It's a three-phase armature circuit, while on the part on the left is the field circuit. The field circuit is supplied by a DC voltage VF, and it has these three components: the adjustable R, and then RF, and then LF. The adjustable R is used to allow us to control the field current. By changing the value of this resistance, we will be able to change the field current, and therefore by doing so we can also adjust or control the magnetic field, the rotor's magnetic field. And on the right hand side, for each phase of the armature circuit, we have what, as we had in the on the previous slide. This is showing that the EA1, V pi is equals to EA1 minus JXSIA minus RAIA. And a synchronous generator, as the other three-phase system, can be connected in Y configuration or delta configuration, and therefore the relationship between the terminal voltage and phase voltage will be different for each, as we have learned before. So for the Y connection, Vt, or the terminal voltage, is equal to square root of 3 times V pi, while for the delta configuration, Vt is equal to V pi. For balanced loads, when we want to do the analysis, we can use the per phase equivalent circuit, again as we have seen before. For the three-phase system, we can have a per phase equivalent circuit that will simplify the problem and will make it easier for us to do the analysis. So this is shown. So instead of the three-phase, we got the per phase equivalent circuit. For the analysis of a synchronous generator, phasor diagram can be useful. From the equivalent circuit here, the per phase equivalent circuit, we can derive again the KVL equation as for the armature circuit as EA equals to V pi plus IA in bracket RA plus JXS. The phasor diagram are different for depending on the whether the power factors are unity, lagging, or leading, as shown here. So the first one that we've got on this slide, this is a phasor diagram for a unity power factor, i.e. the load is purely resistive, and this can be recognized if you look at the IA, is in phase as the V pi, right? And then from here you can see that EA, the internal generated voltage, is larger than V pi, the phase voltage. Okay, and the second one we have in here is for the lagging power factor, i.e. we've got an inductive load, and here we can see that again the internal generated voltage is larger than the phase voltage. Okay, and another thing that we can see from this, that is a lagging power factor, means that the current is lagging from the voltage. So that's why we got this negative angle for the IA, which is different. If you look at the next diagram, the IA has got a positive angle, which means that the IA is leading than the voltage, and therefore we've got a leading power factor, which indicates that we have a capacitive load. Okay, and for the third one, it's possible that the internal generated voltage EA is smaller than the phase voltage. Okay, right. Okay, another thing that I need to mention, I think the JXSIA, because of the J here, that's representing the imaginary part, is always perpendicular to IARA. So it's always perpendicular. Similar, that's for the lagging power factor, and this is for the leading power factor. And similarly, if you look at the previous slide, that you will see that JXSIA is perpendicular to IARA. So if you are asked to draw one of these phasor diagrams, you should make sure that the JXSIA is perpendicular to IARA. and the angle of IARA itself depends on the angle of IA. Yeah, so this angle here depends on this angle. Yeah, okay, and then you draw the j-axis IA being perpendicular, and then finally then you can draw the EA connecting the origin to the end of the vector j-axis IA. Okay, and then for a given field current and magnitude of load current, the terminal voltage is lower again, yeah, for lagging loads and higher for leading loads.